Hello, our today's tutorial is the design of planetary gearbox. As you see, this is our required gearbox. This is the input shaft and this is the output shaft. We achieve a gear reduction in this gearbox. For example, if a certain RPM is given at this shaft, the output shaft will result in a reduced RPM and high torque. What happens inside this gearbox? Let me show you by showing the section view. Okay, this is the section view of planetary gearbox. We can see that it has 4 stages. By stages we mean it has 4 epicyclic systems, and the gears shown in yellow are called the internal gears or the ring gears. As you can see that there are 4 ring gears, that makes it a 4-stage reduction planetary gearbox. The power comes from this input shaft. This input shaft drives this sun gear. We call this central gear of every stage the sun gear. The sun gear tends to rotate the planets around it. Let us open this stage in a separate window. Okay, this is only the input shaft. This input shaft drives this sun gear. Let me show you how this sun gear is connected in the first stage assembly. Let me open the stage 1. Okay, this is the stage 1. I will show you how every stage works. This stage at the moment is not including the input shaft. Let me also import the input shaft to this. We go to this low speed gearbox and insert this input shaft into the stage 1 just to demonstrate what happens in every stage. Let me repeat. Okay, here comes our input shaft. The power comes from here, from this input shaft. This input shaft rotates. This makes these planets rotate. The outer sun gear or internal gear is bolted to an external case which is fixed. So this tends to rotate these pinions. These pinions start walking inside this ring gear. Okay, and now due to rotation of these planets, this arm rotates. This arm is bolted to the output shaft, and as a result output shaft is rotated. This gives some reduction in the speed. Now by stages I mean now let me show you what happens in the stages. The first input comes from here. From here output is obtained. This output becomes the input of second stage, and this is the output of second stage. The output of second stage becomes the input of third stage, and output of third stage becomes the input of fourth stage. The output of fourth stage is our final output. Now I will first show you the design of a single stage. We will then assemble the other stages directly from this assembly. I will show how to independently design an epicyclic gear train. Okay, Where to start? The basic step of designing the planetary gear train is the kinematic design. You should have an idea how much reduction you want to achieve in a single stage. Okay. We go to a new part. We make a sketch on the front plane. Just I am giving a small example of kinematic design. Let us assume that 80 millimeters is the radius of outer gear, so its diameter comes out to be 160 millimeters. Let's say this is the pitch diameter of ring gear. Then this is the pitch diameter of sun gear. Let's say this is 80. So what is the distance between these two? This is 40 millimeters. So the diameters of the sun gear should be 40 millimeters. That's how the planet gear rotates around the sun. Okay, now I will show you the use of toolboxes. Let us now make the use of toolbox. We go into the NC metric standard, power transmission, gears. Let's say we pick spur gear, as spur gears are used. Give me a moment, it should be done in the assembly environment. Okay, so let us introduce a spur gear here. Here is our spur gear. Let's say we take its module 1. Being an engineer, you must have knowledge about the modules, the AGMA standards. I am assuming that this course is for gear design, particularly the engineers are watching this video. I am assuming that you are already familiar with the module system. I do not want to go in the details of module, as I have to cover the whole assembly in this one tutorial. Okay, let us have the number of teeth of this sun gear be 80. Now we will keep the teeth ratio according to the pitch diameters we calculated earlier. Okay, it has 80 teeth. Now I will import the ring gear. In that ratio, the ring gear should have 160 teeth. Increase the outer diameter, that should be greater than 160. Make it 170 for now, like so. Done. We will make their faces in one plane, make them concentric. Now I will add an axis using the reference geometry and selecting any two planes. I would prefer top plane and front plane. The axis appears. Now to show the axis, I made the axis of this gear and the axis I just created. Okay, it says that it is fully defined. I just forgot to remove this fixed constraint from the gear. I click on float and then I try to make them again. Now when I made this axis, it comes to this position. Okay, now I made its face with this plane. This is right plane. Okay, fine. Now let us recall what did we calculated. The radius of planet gears. The radius of planet gears were 40 millimeters in dia. Let's say if I make it 40 millimeters, being in first module the pitch diameter is exactly equal to the number of teeth, so 40 millimeter corresponds to 40 number of teeth. This is only valid if I select the module 1. For module 3, it gives the triple size with the same number of teeth, and with the module 4 it gives the 4 times bigger size with the same number of teeth. Module is basically the ratio of pitch diameter divided by number of teeth. So for module 1 the pitch diameter and number of teeth are same. Okay, let's have module 1 and number of teeth be 40. Okay, now you observe that this size exactly will fit inside these two gears. Okay, now we need some method to constrain its circle just like in this region. I mean, for example, on right plane the gear must be rotating at a circle that is the mean of these two diameters. It should be, the mean comes out to be 120 millimeters. Okay, now the center of this circle stays at this imaginary circle I created, the mechanism would function as it is desired. For that purpose we create the arms. Now the arms which are connected to the output shaft, we made the planes. Now in order to create the arm I make a new part right here, just trace over it to make sure. I make it a triangular part, a slightly bigger triangle than this circle. Just to keep it axis symmetrical, the triangle should be equilateral to keep it balanced during the rotation. So this is equilateral and the median of triangle should be at the center of the gears. How we find the median? We join the vertices of triangle with the opposite line. The intersection of these two lines give the center of the triangle. I move this to this point. I shorten the triangle to this size. Make any fixed dimension, let's say 120 millimeters. I make circles in the triangle right here, let's say be it be any dimension. Now I circular pattern this feature, entities to pattern, about the origin, number 3, done. Okay, now I extrude this triangle, say 5 millimeters. Done. Now since it was created just over the plane, a mate has automatically been created. I just remove this mate and make this triangle independent. Okay, now the center of this triangle, we should have a hole there as well. To assign it a center. Done. Now we made the circle here, keep it some distance with this, let's say the distance be 20 millimeters. Like so. Done. Alright, this should be connected to here. Fine. And these are linked with the shafts and through bearings. I mean, this gear is free to rotate about its pivot. Let's say we have a shaft. I slightly increase the size of this gear. Now the size of the gear, basically the nominal shaft diameter, be 10 millimeters. Done. Create a shaft right here equal to this. I am just doing to illustrate the basic mechanism the epicyclic gear train follows. Okay, now the bearings, ball bearings, radial ball bearings. One on each side. Okay. These bearings are present here just to keep the motion of this gear independent of this shaft. This arm positions the center of this gear, but this gear is not locked with the arm. This is pivoted to this shaft of the arm to keep it free about its own axis, so that it can walk around the internal gear. Okay, do I have the necessary constraints? Yes. Okay, now one more thing, I circular pattern this feature around this 3 times, and I will also select this shaft I just created and the bearings as well. Slightly reduce the diameter of this to have these bearings being press fitted. Okay, done. Okay, now I have the necessary constants. Now I have to introduce the gear mates to make this mechanism work. Then I will show you. Okay, this can rotate. This is basically connected to, I will insert a new part here. Both directions. This is the input shaft, and this is, insert another part. This is the, here the output is derived. That's fine. Okay, now by mates I define that this shaft is locked to this gear, and this shaft is locked to this carrier plate. This is called the carrier plate because it carries the pinions around the sun. These are called planets. This is called sun. Okay, I think I failed to create the mates. I again do the same. This is done. Lock. This is done. Okay. Now when I rotate this shaft, the gear rotates. Mechanically, this shaft is locked to this gear by a keyway. Mechanical engineers should be familiar with the keyways. And this shaft is bolted to this carrier plate, so these are also locked. Once I show you the basic mechanism, we will go into the detailed design as shown in the model first, the target model we want to create. Okay, now I introduce the gear mates. I will go to mechanical mates, gear mate. I will mate this gear to this gear. Ratio I will adjust myself, as it has 80 teeth and this one has 40 teeth. Let's see if it is working or not by rotating. Yes, these are working perfectly fine. Okay, now I have to create the gear mate with the ring gear. Mate, mechanical mates, gear mate, this gear with this gear. This is 40, this should be 160. We maintain these ratios according to the pitch diameters. Okay, let's see how it goes. This happens when the outer ring gear is free to rotate. The planet gears idles at their positions, and this results in a neutral gear and results no output motion. In our case, the ring gear is bolted to an external case which is fixed, which means that we should fix the external gears. Now I have put the fixed constraint here on the internal gear. This F indicates the fixed constraint. Now if I rotate this in any direction, the gears will start walking inside it like this. That explains the basic mechanism of epicyclic gear train. Now the speed by which this shaft is rotating is higher than this. As this shaft rotates, this carrier plate rotates, resulting in the rotation of this shaft. And if we go into the motion study, motion analysis, we give this, let's say 10 rpm, and simulate the motion. And we calculate what is the motion output here. Displacement, velocity, acceleration, angular displacement, no, angular velocity, magnitude, this phase with respect to the fixed reference. We create the plot. The result comes out between 20 and 28, means it is 20 degrees per second. It means let's convert 20 degrees per second into revolutions per minute. 20 degrees per second to convert revolutions per minute. We divide 20 by 2 pi, which is 6.28, and multiply by 60. Wait a second, I must be doing something wrong here. Let me plot the two on the same graph. Displacement, velocity, acceleration, angular velocity, magnitude, this shaft with respect to this, and add to the existing plot, the plot I already created, and now I see the results. Show plot. Okay, okay, now this scales comes from for the one graph, and this scale comes for the other graph. The 20 degree per second one is the output shaft as we measured earlier, and 60 degree per second is the input shaft. So we see a reduction of 1:3 from input to the output. So we have achieved the reduction, which results in increase in torque at the output. Now what is meant by stages? This, let's see if I copy the whole thing. I make an assembly. I randomly save this. I just want to tell you that what happens in the multiple stages. This is just a single stage epicyclic gearbox. What happens in the multiple? I copy, make assembly, from assembly I put this assembly here, I copy this assembly, like so, another copy. Okay, now let's assume that this input is rigidly connected to this output. So the input of the next stage was the output of previous stage, and it results in further reduction. For example, if we place such similar 3 epicyclic trains in series, then how much would be the reduction? For example, it was 3:1 in the first, and in the second it is further divided by 3, and in the third it will be further divided by 3. It means that we will achieve 1/27 reduction in the speed, and the torque will be multiplied by the 27. Okay, this was the basic concept of planetary gear train. Now we will come towards our target model. We will exit this, as this was just for the explanation of the epicyclic gear train. Now we come towards the original assembly. The same is here, just it looks complex just because it has more perfect engineered geometry of every part. The proper bolts have been shown here, fixing the assembly to the case. Bearings have been shown. Okay, now in order to model this, we start from the input shaft. Okay, where is the input shaft? I just want to start from the beginning. Planetary gearbox. Okay, this is a planetary gearbox. This is the casing of the gearbox. It has been divided into low speed and the high speed. In the low speed section, there is the only one stage that is included, and in the next subsequent stages, the subsequent stages are included in the low speed, sorry. It starts from the high speed and goes to the low speed, as you can see in the feature manager design tree. Let me show you the feature manager design tree of this assembly. There are mainly the nuts and bolts and the washers. Just look at gearbox low speed, gearbox high speed. This is the input side, as at the start the speed is high and it starts getting lower in each subsequent stage. This has the highest speed, and this has the lower speed. Then next has further lower speed, and output has the lowest speed. Okay, This whole assembly is axis symmetrical, so making the housing is not a difficult task for this. We just copy the geometry of this. We just don't need to copy the geometry, we make its geometry according to the gear that is included. Now to get the information about the gear, we have this gear here. Let's design the high-speed gearbox first. We go to the new assembly. I exit what I opened previously, this assembly. Now in the new assembly interface, I will create the gears as in this assembly. Okay, by clicking on the gear I get the information. This is from the metric with module 3, 120 teeth and 20 pressure angle, 10 face width. So this gear can be created easily. This is the data I have with this gear. And the one thing to be noted that the module thing, all the gears that are meshing together should have the same module. Module dictates the size of a teeth. If module is different, the gears will not be able to mesh together. Okay, this is the input shaft. We see the design details of the central gear. It has 80 teeth, 10 face width. It has 120 teeth, 80, 120, 80, 120, and this pinion being the shortest has 20 teeth. Okay, this is the kinematic design done for this first stage planetary system, and this is the output shaft of this. Okay, now where to start? We start from making the first stage planetary gearbox. We go into the assembly, okay, in this assembly I import the gears as required. The sun gear, it had the module 3, number of teeth being 60 and face width being 10. We will adjust nominal shaft diameter later and the keyway configuration later. We also import the internal gear, which had 20 teeth, 120, sorry. Number of teeth are 120 and 120 into 360, so the outside diameter should be greater than 360. We make it like 370, or must be 400. It will look nicer. Okay, So we have the ring gear as well. Now for the planets, we choose a 20 teeth planet. It is here. Okay. This should float. I might made a mistake selecting it having 60 teeth rather than 80. It should have 80. 80 plus 20 plus 20 should be 120, equal to the size of external gear. It should be 80 teeth. Done. Okay, now the size is okay. The first stage gearbox is almost done. We join it. Okay. Next, we will see what is the okay. It has a keyway inside and a hub extended on both sides. Let's see what is the nominal shaft diameter. It is 11.25 millimeter. It means it is 22.5 millimeter diameter, and the hub diameter is 7.5. The face width was as expected, it is 10 millimeters, so we add a 7.5 millimeters hub here. Add a toolbox component. We select here hub style both sides. Okay, I do not remember the hub diameter. That is also unimportant as well, as we will not go into those details as in that drawing. Okay, the nominal shaft diameter is okay. We have a keyway also. Nominal shaft diameter is around 22, and keyway rectangular one. That's keyway. That keyway is used to lock the gear with the shaft, the input shaft that comes inside it. Now this is done. I will see the details of other gear. This also has hub on both sides. The hub diameter is approximately equal to the internal, or we can say that dedendum diameter of the gear, inside diameter, or this is called the inside diameter, this is called the outside diameter, and the line along which the gears mesh somewhere lies here is called the pitch diameter, that the diameter that is formed around this circle. Okay, to see the details, it has nominal shaft diameter is 37 millimeters, and this is larger just because it has to carry the bearings inside it. This is 42 millimeters. So I will edit our gear. We will go into the assembly, edit our gear according to the requirement. The face with 10 is okay. The hub style both sides. Hub would be slightly shorter. It should be around 60. No, 20. 20 is too less. I'm just guessing. Okay, 40 looks fine. 50 would be perfect. Oh yes. Nominal shaft diameter is 37 millimeters. The nearest one, I choose the nearest one. Now there's no option to directly create the step inside this. There was no shaft since keyway, since it is not required to be locked. It is on the bearing with the arm, the carrier plate that drives it, that carries these pinions. Okay, the overall length should be 10 plus 7.5 plus 7.5, that should be 25. Okay, I make it 25. Okay, now that's nice. I will make this 25 as well. Okay, I am skipping the step of creating another cut here to carry the bearings. The step is created just because that bearings that are inserted will not slide in one direction, just for the axial retainment of the bearings. I insert the bearing here. The size of the bearing should be and go towards the smaller sizes. That should be around 42. The outer diameter should be slightly higher. Okay, that is around some nice value. Thickness should be little less than 17 millimeters. 17 sounds too much. Okay, that's not. This is having lower thickness. Just according to the availability of bearings in the market that you can easily access, you should design the internal bore and the stepping of this gear, being a mechanical engineer. Okay, let's assume that it is okay. Just creating it from the very basic. Okay, the bearing comes here. In fact, the bearing comes on the both sides in the actual assembly, and the carrier also comes on the both sides. Now we will continue by creating the carrier. Let's examine its geometry. It has a very simple geometry, and this part can easily be created by the milling process from 5 millimeters plates. Let's see what is the thickness. it, it is 8 millimeters. So we get the 8 millimeter steel sheets are available in the market. Steel or iron or whatever material you want to use, these materials are available. You just make either make them on CNC milling or manual milling. There are many ways. For CNC you have to generate the G code for these contours, and you can easily mill out this part. So this is not such a complex part from even the perspective of 3D modeling, not even from the manufacturing perspective. Okay, let's examine its geometry. These circles are 272.4 millimeter radius, and the center circle is 72 millimeters. 272. Okay, that's fine. I can easily create such part. Just the important thing is the distance between this circle and this circle. The center of this circle is 150. This is the basic kinematic design of this carrier plate. Okay, we go into the new part. First we make a circle, make it around 200. Create the other circles here. Keeping the size to be 272 millimeters, and I think it should be, that was radius of 272 millimeters, it should be more. Anyways, let's continue towards the design. It should be 272.4 into 2. That's how it is. We make it circular sketch pattern. Entities to pattern is this circle 3 times. For battery tuning. Okay, that's fine. We have to create circles and trim the outside thingy. Make it further. Okay, that's fine. Just make it a distance from here, be it 320. Okay, that's fine. Let's trim the unnecessary part of the circles. So here, oh, I made a mistake here. This to create it just at the center, I create line from the origin to the center point of this arc, and a circle on this. Fix this line and dimension of 150 millimeters. Okay, it was 150. Again made some mistake. It should not be fixed. I unfix this line. I increase this distance. I should increase the radius of this it should be 400. Okay, a little less than 400, 380 maybe. 350 might do the trick. Okay, that's fine. Make it further away from this. 4 becomes too much. 350. Okay, that is fine. We slightly increase the size of the circle. Let's make it 30 millimeters. Pattern it around the center point. That should be 3 in number. Okay, done. The carrier plate is almost finished. The extrusion was 8. Okay, just adding fillet to make it look better. Let it be 5 millimeter fillet or 4 millimeter. Okay, that looks fine. The center point, this was 72 in diameter, as I remember. 72. And for bolts it should be something like this. Okay, this thing is done. We go into the main assembly, insert components. I think I have not saved the part yet. I save it as part 6. I'm not naming the part as this is not necessary at the moment. You can make the nomenclature at the end of the project by modifying the names. At the moment of design, you should only concentrate on design to make it perfect. Okay, now here comes our carrier plate. This not being constrained as concentric. Now it is. Okay. This is basically on the both sides of this, on this as well as on this side. So we mirror this part about this plane. Let's see how it goes. It goes excellent. Okay. Let's see what we have to make. This two-sided one, how in the section view, the one side is connected to the shaft, and the shaft other side is connected to the output. The ring gear is bolted to the external housing. Okay, so we are almost done. creating one of the stages. The next stages are also created in the similar manner. We will create a shaft and bolt it in this area, and we will create another shaft and bolt it in this area. So the mechanism will work. These planets need to be patterned around the center 3 times. That is not a big headache. I must do it right now. Okay, like this. Okay, now one thing that remains is the housing. Let's make the housing. Let's make the complete housing. The housing of this is very simple and straightforward. I will tell you how. This is basically the axis symmetric housing with the bolt holes being patterned around the circle. So these, no matter how much part this has, this can be created by just one revolve command, just one feature. The other feature is for the holes for the bolts. Okay, and now to create this part of the housing, I will show you. Just let's say I sketch in this plane, convert entities. I directly pick the profile from here. Also from inside, precisely for the bearings. I'm just getting the points. Or in a more easy manner, instead of sectioning it, I create a sketch here, a box here, extrude it, cut it. Okay, now I see this as, I can now easily copy this profile, convert entities, click on this face, done. Just to correct it from here a bit, like this, trim the wrong part out that has just been created due to the ball space. Okay, I will copy this, new port, I will revolve this around this point, just should be a better sketch. Let's see how much the distance it has from the center. The central portion was 25 millimeters, so it has 12.5 centimeter distance from the center, and I create it as I exit this part. Make a center line, keeping it fixed at a distance of 12.5 millimeters. Okay, now we revolve around this line, so one part is created. To create the holes for the balls, we create a sketch here. On this plane here, this can be circular pattern around this disc like this. We can insert balls all around it the way we want. Okay, now since you know the way of creating one of the piece of housing, you can create the all parts of the housing according to your requirement. So I have demonstrated how to create each and every part in this. I do not think anything remains in this. I have told you how to create the carrier plate, how to create the housing, how to create the ring gear, how to do the kinematic design, how to make the sun gear, how to make the pinions, how to create the animation. Now I will use a ready-made part to get this complete assembly again. The only thing I left is the creation of this line, and this is not a big task. This just a extruded cut from this face. Spline can be easily created, and this in this stage the gear is bolted to this assembly. Okay, now I suppress this extruded cut. Now let's start doing this assembly from the parts. I will tell you at the end how to put these bolts directly inside it. Okay, first let's do it without the bolts. We create the high-speed gearbox. I got new assembly. I will show you how to assemble each and every part in one environment. Okay, we search for input shaft. Input shaft part assembly. This assembly contains the gear as well. Okay, I'll just get the input shaft. So we have the input shaft right here. I will close the unnecessary things. Let's see what there's a Timken bearing, input shaft, then key stock, this key is used to lock the shaft. Okay, this is inserted here in the keyway. To show a better view, here the key is inserted in this, then gear is inserted on this keyway, it gets locked with the keyway like this, and then bearing is inserted. Okay, I go back. Okay, I have defined how the input shaft is assembled. So in the assembly, I directly import the input shaft assembly, complete assembly. Okay, now just to tell you how to insert the Timken bearings. You can get those bearings from the internet, from the Timken website. The Solidworks toolbox has SKF bearings, Torrington inch, Torrington metric, and ISO standard bearings, ANSI metric standard, ANSI inch standard. So you have a big choice for bearings. You can find for any bearing of your from this choice, and these are readily available in the market. Okay, let's see which bearing is used in this. This is okay, this is the output. These all are the Timken bearings. In the new assembly environment, I import the input shaft directly. Input shaft here. Let's say that we create a standard axis that we will use in our animation later. We create an axis here, and we start from right plane meeting this shaft here. Okay, this is fixed. We make it float. Okay, here, and why don't you float? Get float. Okay, right plane, this plane is here, axis, turn the axis here, so this is constrained. Let's test it. Okay, so here starts the input shaft. Let's insert the other parts. Let's see what else is included in the high speed side. Input shaft, then stage 1 planet. Okay, fine. Stage 1 planet, then high speed cover, high speed case. Okay, let's insert the high speed cover first. Just align it exactly, make it transparent, change transparency, just fit it where it is. Okay, it comes right here perfectly. Just let's see how it is fitted there. We keep this view. The bearing is aligned with this face, and second bearing with this step. So here's the key point. This is actually the output shaft side of the shaft, and this is connected to the planetary carrier. I might have made the other way around. This is the retaining ring. It is inserted onto the groove of shaft to retain the axial movement of the bearing. Okay, just to align with this step, this bearing, we select this face, then we select this face and this face. Along with the assembly, let's just keep assigning the colors. Okay, the next part is this high speed case. We align the holes. And then make them concentric. This is aligned. Okay, now we get the ring gear. Ring gear stage 1. Fine. Mate. Hide for a moment just to mate this with this, like so. Okay, these are okay, aligning it with the holes. Done. You save it with the new name. Okay. This is done. Just hide for a moment to add the planetary carrier. This complete part should be added, excluding the planetary carrier, excluding the ring gear actually. So this was stage 1. Stage 1, I add the stage 1 here directly just to wrap it up. Insert components, stage 1, planet assembly. Now insert stage 1. We dissolve this assembly to specify the appropriate mates. Okay, this should be fixed, and this should be rotatable. Okay, we are going fine up till now. Okay, we have all the parts. This is unimportant to add it second time. We assign them the proper mates here, here. Okay, delete this other parts as these will be patterned. Okay, let's consider that we have done to this point. Let's just assign the mates. This is fixed, this is fixed, this should be rotatable, but at this should be at a fixed distance from this point, and this should be rotatable about this. This should be here. This should be locked with this one. No, let me correct it. Let me position it again. It will be placed near this point. Alright, just wrap it up by assigning the appropriate mates to each part. We already have a lot of time doing this tutorial, and we need to end it in few next minutes. So I think everything has been explained. You need to model this. Okay, first I fix this, then I made this shaft to its here. From here to a distance. Let's log these bearings with this. Okay, this has already been locked. Let's see what's movable. Okay. The distance now. This should be locked with this lock. Okay, this is a part of one assembly. We first need to dissolve this Okay, let's see what is not connected with this. The pinion should be pulled outside and the ring should be pulled outside. Okay, where's the ring gear? Okay, here's the ring gear. We pull it out of the assembly. We lock this ring gear to this. Now what remains? Okay, pinions are left. Planets. We also pull the planets outside. Okay. So we do not need these planets here. This I will delete. And I pattern this planet around this circle 3 times. Use the gear mate, advanced mates, mechanical mates, gear. This is 20, this is 80 teeth. This is 20, this is 120. Just about into the ratios of the teeth. Let's see if it is working okay. This seems quite fixed. This is the input shaft. Okay. Gears have not been yet retained axially. Okay, we retain them by introducing this mate. This face should be in plane with this. The gears are functioning as desired. This meeting is complete. Now to add further stages, we save this first, minimize this, open the main assembly. To make it function properly, we should dissolve this. High speed, dissolve sub-assemblies. Let's see if it is still working as we desire. Okay, some mates might have been removed. Let's assemble the loose side now. This and this should be fixed. Now we hide them. The ring gear should also be fixed. Okay, there are part of assemblies, stage 3 and stage 4. We remove the ring gear from here. Remove the ring gear. Where's the ring gear? Ring gear from here and from here as well. fix these three. I can fix them. Alright, stage 3. Now what else needs to become out of stage 3? The pinions. Okay, let's start from stage 2. Let's have a mate with this at a distance, then concentric mate so it stays in place. Then I remove this gear. Out of this, okay, this is fixed. Okay, this is now also fixed. Okay, for this one, we move these three out of this. We place the mate here, distance mate, and the concentric mate it should be. Concentric mate, and when this rotates, this with this, this with this, and this with, okay, it is already constrained. we go towards the stage 4. The distance of this should be like so. This should be concentric with this, and this should be moved out. We are moving these planets out of this assembly because they need to spin independently of the carrier plate. We also might left some of them inside. This one is okay. Okay, this one is still inside. I move it out. This assembly, yeah, this is fine. Okay, they are also not independent, so I made them place the concentric mate first, then the face mate for this. Okay, this should also be moved outside, and you place the same two mates here. Okay, I might have done some mistake with this part. ST3 liner shaft. This go inside this assembly. Okay, I messed up with this assembly. Now this is also being corrected. I place the mate here. This is okay now. Place this mate here. This is also okay. This goes okay. There is also a problem here. Okay, this come out of this, and this should be fine now. This is concentric with this, and this is coplanar with this. Okay, this stage is now okay. The last stage remains. Okay, so almost everything is been done. Okay, this creating some problem here. It should be okay. These pins should be separated from this. Parallel pin hardened. I would rather consider deleting them. These are of no use at the moment. Okay, now everything has been done. Let's specify the gear mates to make the assembly work. Okay, let's do the remaining 5 to 10 minutes work, and this will be then finished almost. Okay, this will be the mechanical mates, gear mates, and we are locking 30 teeth and 80 teeth. 30 and 80. Let's see if the direction is right, or we have to alter it. No, direction is not right. We go to the mate and reverse it. Okay, it should be fine now. Let's see. Okay, now it is behaving as we want. Okay, we have to do the same with the others. Okay, now this carrier is the input to the next sun gear. I want to see the sun gear. I hide this temporarily. Okay, here's the sun gear. If I rotate this, okay, this is fine. Let's mate this with this one. Mechanical mate, gear mate, and let's see what is the ratio. It is 20 teeth and 20 teeth. Okay, both are 20 teeth. Let's make it 1:1. Okay, let's see it has got it right or not. Okay, it is perfectly fine. And with external, it should be again a gear mate, 20 teeth width. We have to see 20 teeth width, 60 teeth, 20 width, 60. Let's see if it is fulfilling the purpose. No, it is opposite. We go here and check the reverse. Tick. Okay, it is fine, but there is a slight misalignment. We delete it for a while. Move it slightly here. Choose this face. Mechanical mate, gear mate. This is 20 teeth or 60 teeth. just one last mate. These are 60 teeth and 20 and 60 combination. 20 and 60. Let's see if it is working okay. No, its directions should be reversed. Okay, we go here and reverse direction of mate. Okay, now it is working fine. Just one more thing, we hide this as well. One last gear, made it this as I remember. Okay, I have to gear this one with this. This is one last thing that I have to do. I think this is 20 teeth, 20 teeth means 1:1. Let's see if it got it right. Oh my god. This should be fixed with that. Okay, let's see overall mechanism. This is working around this nicely. This is working fine. Okay, this is not, the third stage is not connected to the fourth stage. Okay, we hide this as well. Okay, so the problem is this gear. We made this with this face, this plane with concentric with this, and now the one last made the gear made mechanical gear. This is the 20 teeth versus 20 teeth means 1:1. Okay, this is now working fine as well. We have done, almost done. Let's see if we start from here, it works. Okay, one last thing, mate lock this gear with this, must be okay. Now this should be connected. Okay, this is taking time to calculate. Okay, now the whole assembly is almost linked and the mates are working perfectly fine. Okay, we can see that output shaft is also rotating. Okay, now the one final step is to dissolve this assembly here. first we unhide the hidden parts. Show it to and the guessing is yet to be shown. Show this one as well. Okay, is it working? Yes, working very nicely. Okay, we are dissolving this assembly now. A big step. Okay, does this work? Here. Instead of doing a lot of work again, we open the same assembly that we were able to achieve the correct mate with. Okay, we insert the high-speed gearbox directly here. Made it here. Now we will dissolve this part. Dissolve assembly. Okay. Okay, now this should be connected to the gear that works. This should be connected to this one. Mechanical mates, gear mates, are they equal? 20 teeth, 30 teeth. Okay, 30, 20. Let's see, we got it right or wrong. Okay, this is fine. The only reason it is not rotating that it is linked with the gear now, and it is taking time for calculations. That is when I rotate this rotate. Okay, now what will cause it to rotate will be the okay, we have already gear made here. Yeah, that is fine. Just we lost a mate here. It should be here. Okay, I think now it will work. It should be working. Let's make it transparent. Okay, see the difference in speed. Okay, we will make the whole assembly transparent and run a final motion simulation. You will observe that every subsequent stage will be running slower than the previous. Okay, now just to join them, I click this face and this face. Being fixed, it does not allow me. Okay, no problem. Something must be, yes, this is fixed. I make it float and make it move. I am not concerned with the balls here. Just want to show you the results of this assembly. Okay, this must go here. Okay, this is fine. Okay, this is fine as well. Okay, just we need to fix this final part now, and the whole assembly is going to work. This is not important. I delete them all. Okay, let's see how it goes. Okay, let's do the motion steady. Make it 12 seconds. Place a rotary motor here. Must be at 50 RPM. It must be motion simulation. Make it like here. Rotary motor. Let's see how it performs. Oh, this is working very nicely. The output shaft is rotating as well. So you can see the high level of reduction this planetary system can achieve within such a small space. The output is almost rotating at a negligible speed as compared to input shaft. This is such an example of high level of reduction within such a compact size. So these were our results. Let's increase the speed of motor or run it at higher speed. Let's say 5x, so we can observe some movement. Look at that. So these are our results. Just we compare displacement, angular velocity, magnitude of this. Okay, plotted. Now this is the plot one, and the results of output shaft, displacement, angular velocity, magnitude. Add to existing plot, plot 1. Done. Let's see the plot results. This is tremendously, this is one is between 1 and 2, it means it is 1.5, and the other is 300, between 300. So we have achieved a tremendous reduction, around 250 to 300 times slower. So that was our achievement today. Thank you for learning. Thank you for following my tutorials. Goodbye.